G'day, Alakar J here. In this video we'll be finishing off our Perlin noise, the fractal Browning motion. We'll expose a couple more variables so we have more control over the output that we're generating. And just to recap what we were doing, we were creating different maps at different frequencies. And each time we went to a new map, this was an octave. And then at the end we added all the octaves together to create fractal Browning motion. So it's easy to imagine as a one-dimensional noise. So here you can imagine we have our frequency. Let's just call that a frequency of 1 at an amplitude of 1. And then for our next octave, we would double the frequency. So we times it by 2, and we'd halve the amplitude. So we times that by 0.5. And then for the next octave, we would double the frequency again, and we would halve the amplitude again. And so on through every octave. And then we'd add them all together and we get this noise, this cloudy noise. So we go back to the code. You see, initially I just had it as gain being the change in the frequency and the amplitude, but here I introduced Lacunarity as a change in rate of frequency. Now similarly we have another factor for the amplitude, and that's called persistence. It's the rate of change of the amplitude. So we're going to start and we're going to code this in. So back to the top, add a couple more variables. Public float Lacunarity. And we were using the default of 2 because we were doubling the frequency each time. And persistence, which was 1 over 2, which is 0.5. And then we're halving the amplitude each time. I forget the F in there. Okay, so you see that I haven't exposed amplitude here as a public variable. The thing is, in our fractal, after we finish generating, even if we just did one iteration, we had the basic Perlin as the output, we are normalizing the output by the amplitude, which is the factor here. So even if we started off with an amplitude of 0.5, at the end our noise would then be divided by 0.5 or multiplied by 2 to give a value between 0 and 1. Again, it's normalized. So exposing amplitude is redundant because we kind of cancel that out here. Now we can use a filter in the future if you wanted to generate a smaller amount of noise. Okay, so now we have 2 new variables. Our rate of change of frequency, that's our Lacunarity, and our persistence, or rate our change in amplitude. So how do we implement that? Well, remember I use a fudge variable called gain, which is kind of taking care of both at once. See, as gain was multiplied by 2, it was used here, and it was using reciprocal, so 1 over, to get the half value here. So we don't use gain anymore. So we start off with our initial frequency and initial amplitude, but we're going to be modifying it per octave. So we don't want to be modifying that initial public variable at the top. So we need to create temporary variables that we can manipulate and use in the equations. So let's create them. Float frequency. The frequency we'll use in the equation start will be our initial frequency. And the same for our amplitude. Amp equals. It would be amplitude here, but as I said, it's normalized down here, so we'll just make that 1. Okay, so where we multiply by the frequency here, this is where we now... let's do the other bit first. Okay, so we're not using gain anymore. But we have these temporary variables. So our frequency through each iteration is multiplied by Lacunarity, our rate of change in frequency. And similarly, our amplitude, that's what happened. The frequency is multiplied by the lacunarity, and the amplitude is multiplied by the persistence for each octave. So now we have this value here. Okay, let's all do it sequentially. So our frequency, instead of now being this, alright, so now we just multiply it by our modified frequency depending on the octave we're in. The same here. And here, where we're modifying it by the current amplitude of this octave, we'll use this. And then the same for our normalizing factor. Like that. For our normalizing factor, we add the current amplitude that we're using as the maximum possible value we could get through that iteration of the octave. Okay, so it's pretty much just doing exactly the same thing. But now we've exposed this frequency. Sorry, we already had that. Now we've exposed this lacunarity and persistence, so we can create slightly different maps. Let's create a test. Let's take the first one. Full fractal. Okay. Change this to our fractal. Now, this is initially the same variables we had, 2 at 0.5, frequency of the initial frequency of 1 for 4 octaves. So if we hit play, wait for Unity, we get our output. Now, okay, let's just use grayscale. So we have our cloudy back. And as I say, you can use our offset here. We can get a different area. Okay, so let's create a good sample. That's not a good sample. Okay, and let's see what happens if we decrease the lacunarity slightly. Completely different output. That's because when we're adding, each time now we're adding on the noise, we're not completely doubling the frequency. This is slightly different. So if we're adding different frequencies each time, we're going to get a different output overall. We'll just increase the initial frequency. Let's see if we can get a bigger sample size. Okay, so again, 1.81. Let's see if we can get a slight change. Again, it's very hard to tell unless I brought out all the other ones and saw what we were adding up each time. And then similarly for the persistence, if we brought that up, we get a much larger change. You see what we're adding more and more of that higher frequency octave, the higher the persistence is. Okay, as I say, with the lacunarity, we're not doubling the frequency, we're adding 2.1, we're multiplying by 2.1 each time, so we get a much different output. So lacunarity will greatly change the overall output, where persistence is more of a fine-tune on the type of output you're getting. Okay, so what we're going to do next is, now that we've got this full fractal Browning motion function, we're going to wrap it up in its own class. So anytime in the future where we want to have a project and we want to implement our fractal Browning motion, we just carry this class that's already pre-written. It's got one job, it does it well, bring it into the project, call upon it, and ask it to spit out some noise for us. And then we can move on to making height maps and going to terrain.